Do you see my presentation now?
No, I'm not. It's not coming through. Let me see.
So I tried to put it on one side, not the other, but I have like this much window. So I was going to cut the film out, put one on this side.
Is it clear now? Jason?
No, it's not. Can maybe Shomo share and he can
Sure.
change the, okay. Why don't we try that?
Sure, I can try to share this.
Okay, go ahead. I've gave you the presenter.
Thank you, sir.
Thank you.
I don't see anything yet.
It's coming up. So let me know when you can see the screen, guys.
Okay.
Try it again.
There it is. Just make it full screen and I think we're good.
Are you sharing? I don't see anything.
Yeah, I did full screen.
Does everybody else see it? Because I don't.
Yes, it is up, Neil.
Okay, well, I guess I'm going blind here. Nice to start there. Nothing like a little bit of stress to start off the presentation. Tried 20 minutes to log in. Anyway, my name is Neil Johnson. Thank you, Jason, and thank everybody for joining us. I'm going to go a little bit blind here, and so Shomo help me out in terms of what page I'm on. I should be on page number 1 right now. I'm the senior principal at the Global Research Center in Schenectady, New York, and I'm the team leader for the American Makes program for the Feature-Based Qualification and Directed Energy Deposition. Today's presentation is our program closeout presentation for the American Makes members. This will be a team presentation, as I'll be calling on a couple of my colleagues, the GE colleagues, to present along with me. But first, I'd like to sort of acknowledge the overall team and key contributors and partners on this effort. You know, Edison Welding Institute, from the Edison Welding Institute, we had Lee Curran, Dora Chang, Brad Nagy, Alex Kitt, and they were really primarily responsible for doing all of our builds and some of our testing on this program. From Youngstown State University, we had Eric McDonald, Ronald Yarwood, Troy Collar, and of course, we're missing a name, which was really Corey Brosnan, who helped us in the thermography and in the workforce development part of the program. And I'd like to acknowledge both the GE Aviation and Additive, Chris Williams, and from Raytheon, Jeff Schubert, who really were our industrial partners to help guide us in terms of what was important and the direction that really made sense for the aviation and the aerospace industry. Of course, I'd like to acknowledge and thank Tom Broderick, Mark Benedict from the Air Force Research Lab, and of course, Brandon Rubik and Dave Siddle from American Makes in terms of sponsoring the program and some of the discussions that we've had along the path. On the GE research side, we had, I'm going to start from the bottom actually, Genghis Khan, who was helping us out with statistical analysis and model development, Shungji Cheng and Satya Raghavan, who really helped us with the design and some stress analysis that we did. And then the core team that we have, the top 3 members really were Shomo Nag, who was co-leading the program and effort with me, and really is the chief metallurgist and did a lot of the design for experiments and setting up and guiding the entire program along with the efforts of Yiming Zheng, who actually did the model building, and Srikar Karanati, who was really responsible for data organization and vetting the data, and also helped a lot in the design of the experiments. So having said that, you can go to page 2. The total funding for this program was, from the government, was $2.4 million, with a total cost share of about 2.1, with a sort of a rounding of about $3.7 million. The period of performance here was from June of 2018 to originally June of 2020, and then we asked for a 3-month extension to, tidy up all the loose ends with the report and the model, and being able to do all these report outs as well. Skip to the next slide. See if I can get through this. The problem statement for here was really, most everybody is aware of how long and tedious path for certification to be able to go from a concept part to a production part using additive manufacturing. The idea, and typically you choose a set of process conditions. After you design the component, you choose a set of process conditions, you build it, you cut it up, you test it, and you reiterate a number of times on that. And that's really what takes so long in terms of doing it. The objective here was to see if we could develop a model-based predictive model that would be able to predict based on linking process parameters, additive characteristics of the feature that we build, and the material property relationships, so that we could reduce the amount of time that it would take to actually, be able to go from concept part and actually qualify the part in production. So in today's presentation, what we're going to talk to you a little bit about is the overall problem statement, like I just told you, the overall technical approach. I'll provide you an example with a concept part to how we identified the features of interest, provide some description about the design of experiments and the build of those features, how we extracted some test samples from them, and give you an overview of how we organized and conducted some preliminary reviews of those test sample data and material characterization of it, and then provide you with an overview of the predictive model and how we built it and use of it. So Shlomo, if you want to go to page 4. So this is a pictorial example of the project, where we started off with a part design, with a representative part from the aviation and aerospace business, and then we built that. We identified and extracted the features of interest that were critical to that part, as you can see in the second picture in the middle, where you had feature extraction. Then we designed a build process DOE around those features. We then built them on the additive machine, and then we sampled and we cut sample coupons out of those builds, and then tested them and characterized them, and then provided those to that data matrix, and built a predictive Bayesian hybrid modeling GUI interface for that. With that, I think I'm going to hand this off to, I'm sorry, next slide. I think, so what I failed to tell you in the beginning was that the DED process of interest is a laser blown powder process, and it's primarily made by RPMI, and it was the 577 and we built this with, that's located, actually, the facility that we used was at EWI in Buffalo, New York. And here are the process parameters, or the process capabilities for that equipment set that we were using. The powder that we were using in this particular program was Ti-6Al-4V, and it was a powder set that was about 50 to 150 microns in diameter. Shlomo, do you want to pick it up from here and tell them a little bit about the concept part and the building process that we did?
Yeah, sure. Thanks, Neil. Good afternoon, everybody. So based on what Neil talked about, the technical framework was to have an initial goal or to build the HPC part itself based on some legacy build parameters. The different sections of the part, as you can see, are built via different deposition strategies. We were fairly successful in our starting build, where some parts build very nicely, while not so successful for other sections of the. But our overarching objective was to identify different features which are critical towards the performance of the part, which is the HPC here. The chart you can see here talks about the different features of interest that we can talk about here. The first feature, which is the most simplistic of them, is the thin vertical wall feature highlighted in blue. The features 2 and 3 are really the variants of feature 1, where we have discontinuities or intersections of thin wall structures. So feature 2, the one you highlighted in red here, is a hole that you can build. We cannot build by vertical build orientation, so you have to change the build itself. But for other builds like rhombuses and the teardrops, the ones that you see in the bottom, that you can actually build with a single build orientation. So we chose those as the hole of choice in terms of geometry. For feature 3, we looked at the intersection of different wall thicknesses interacting with each other, trying to understand the thermals, which would result in different property structures. We kept one of the walls to be vertical and the other wall built at incline with respect to the initial wall of interest. So for each of the 3 selected features, we went through a progression of the build schemes, the stress predictions, the sample extraction strategies, and finally the build execution part of it. So you can see there are line items for each of the 3 features from left to right as we go from one set to another. So we're going to talk about all 3 of these features, more so about the wall feature, which is the simplistic one, and which is the basis for the next 2 features that we're going to drive along. So from the basic part of the feature, like I mentioned, we start with this basic feature, which is the thin vertical walls. We start with the dimension of the wall of choice. So what we looked at is have the wall of 6-inch tall, 10-inch long type of dimensions, and then the wall thickness governed by the beam width with the overlapping beads for the single or the triple build strategies. For the C+H or the contour plus hatch type of build strategies, we ended up having similar wall thicknesses in terms of our targets. So the first thing that we did was to understand the stress states that the wall would see if we make a wall of this sizes. We understood that there could be effects of warpages, there could be an effect of high stress locations leading to cracks. So that's what we did some simulations on them. And then we went forward in terms of extraction strategies, exactly where in the wall we are plucking the samples out of, what is the orientation with respect to your build axis, etc. And then once we had a clear identification of these schemes, we finally went through the build execution, what you can see in the bottom left, different walls with different thicknesses being built in this DOE. So we go to the next slide. Once we build the walls, we actually wanted to have an evolution plan, right? So we have a layered matrix here connecting the X's and the Y's. So we have things like build parameters, post-processing, and the extraction strategies connected to the evaluation of the build DOEs. So things like the build characteristics such as wall thicknesses, build times, vertical usage, etc., can be directly connected to the build parameters like power, speed, feeds, beam diameters, etc. And so if you go one level deeper, quantifications of the defects in the microstructures like lack of fusions or gas porosities or the latch sizes or the grain size, etc., all of this can be connected back to the build parameters, but also with the post-processing steps. What kind of heat treatment the part sees, what kind of location that you're taking the part out of. And then the last layer down is the mechanical property understanding, which actually takes care of all the above items in the X's, but also looks into the sample extraction, what is the orientation of the sample with respect to the build direction, and also if the surface had a machine surface or not. So all of this together, we had about 15 different build parameters coupled with different build strategies, 100 plus panels characterized, 250 plus tensile tests. And we were able to obtain a unified model connecting the processing structure property assessment via a data-driven approach. So let's talk about the DOE for this the feature 1 here. So you can see that what we executed in this particular feature, we had a wide range of parameters intentionally developed, ranging from a power setting of about 400 watt to 2 kilowatts, tool paths being single to triple to C+H's. We kept some of the parameters constant, to have a manageable DOE. Things like nozzle geometries and focal distances were kept constant, where obviously speeds and feeds are going to change based on the beam diameters and the power that you use. So the columns on the right of that table here, you can see that roughly two-thirds of the samples were left in the as-built plus stress relief conditions, while the remaining one-third was in the fully heat-treated conditions. The heat treatment schedules are in the bottom. One thing I want to share here is for the stress relieving heat treatment, we kept the build to be the heat treatment to be done at a much lower temperature than what usually Ti-6 sees. This was intentional because we wanted to achieve 50% stress relieving so that we can keep the build memory in terms of the microstructure intact without fully cracking the part. So when we liberate the part from the substrate, it shouldn't crack, but it should have, so the stress relieving should be enough to not crack the part when you relieve it from the substrate. But at the same time, it should not forget the microstructure that was generated during the solidification and post solidification solid state transformation processes. And then the HIP and the heat treatment was done by a standard Ti-6 heat treatment as per the titanium handbook requirements. So changing the gear a little bit here, the next few charts, we're going to quickly talk about the different characterization tools that were employed for the evaluation of individual microstructure and defect characterizations. As you can see in the chart, it compiles what we are measuring with the measurement units. Again, I must note that the focus was to generate quantitative values of representative microstructures that could be directly fed to the model with no qualitative bias. So no good, bad, ugly kind of a bias in there. So all numbers, right? So we did, tons of data generation, but I'm going to highlight a couple of important findings from this work, which I can share in the next couple of slides here. What you can see in this chart here is a nano-CD evaluation from the left to the right. You start with a 3D scanning with the void identification, visualization, and quantification. We have kept the coupon thickness to be constant, just to make sure that we are looking at the same interaction volume. The resolution of this is about 6 microns per pixels, and it takes about an hour to image these. So they were really quick turnaround. It was very clear that the C+H's, the contour plus hatch build strategy showed the highest amount of porosities. So it was a clear indication and a powerful technique of nano-CD, where we could not only ID the type of defects, we could visualize the defects, get the number density as a function of distance from the surfaces, and also correlate that with the build strategy, which was, I think, a great insight. And realistically, for thin wall builds, you can do it for in a non-destructive fashions also. The second part I want to point out is the quantification and the determination of the orientation of the lathe structure here. So, so as you can see on your left, there's a comparison of statistical distribution of the HCP alpha lathe size, as well as the lathe distribution for different heat treatments. So on the top left, you have the as-built plus stress relief sample, and the bottom left, you have the fully heat treated sample. You can see that the average lathe size has changed, but also the distribution of the lathe has changed during the heat treatment, which is a great deal of information which we didn't have before. Similarly, on the right, the colorful maps that you observe is due to the crystallographic orientation of the alpha phases. So this clearly exhibits a 45-degree texture of large-scale alpha lathes with respect to the build directions. So this was a significant finding because this will be impactful in some of the property data that Shrikar is going to share later on here. One last aspect of the microstructure before we talk about the property data and the modeling outcomes here. Usually there is a multi-level connection and contribution of the microstructural factors that yields the observed property response, no pun intended here. So there are different hierarchy of the microstructure, which I've highlighted here, which actually compares or correlates with the yield strength. So things like alloy chemistry, where you have the starting powder composition with the bowl, the post-build chemistry and the post-heat treatment chemistry, how the major and the minor elements change with the post-processing is something that we have to keep in track. phase fractions, right? So when you do the particular heat treatments, the alpha and the beta phases fractions, along with the fast cool one sides and possibly alpha 2 phases, are of interest from the Ti-6-4 side. Grain sizes and grain anisotropy. So here the Hall pitch effect comes into play. So the image that you can see here are very anisotropic grains grown more elongated or columnar along the build direction. So that would change to have varied property along the vertical and the horizontal directions. And then taking one level deeper, we talk about this basket weave versus a colony microstructure in Ti alloys, which is really a dependency of the cooling rate. But even when you have basket weave microstructure, like you see on your right side, you have the very fine scale fine scale feature size, which is more monolithic in structure, versus a more relatively near to equilibrium microstructure, which is more alpha beta structure. Similarly, having a basket weave structure, but the yield strength contributions would be very different between one versus the other. And the last versus not least is where we could get in the alpha lat width and the aspect ratio part of it to be able to threshold these numbers, and then using it through the deep learning tool that we have generated. That was really an important piece of information in terms of quantitative values that was added into the Bayesian hybrid model. So in the next charts, Shrikar will walk through the mechanical property response of the thin wall feature, which is the feature 1. Shrikar?
Yep, thank you, Shoma. After the characterization, both mechanical testing and otherwise, we pulled the data together and we performed a first order analysis to make sure if there were any possible trends, and if there are outliers, try identify them and make sure the data is reasonable. So here on this slide we have a summary of the mechanical testing data, where data from all the different process conditions was pulled together, and then we segmented by test orientation, meaning the gauge orientation with horizontal during the tensile test, and surface condition. So here we've looked at specimens with as-built surface condition on 2 faces of the gauge volume and fully ground surface finish on all 4 faces of the gauge volume. So these were flat dark bone tensile coupons, and then the heat treatment effect. So in the as-built and stress relieved, and then hip and aged. So comparing this data with reference to as cast values from ASTM handbook, the red dotted line here are the handbook as cast values for reference. So one of the biggest takeaway here is the anisotropy in strength performance with different test orientations, with 45-degree orientation relative to the horizontal being the largest. And the heat treatment effect is also apparent here. So upon heat treatment, we see a substantial drop in median strength values. However, the anisotropy in the material doesn't appear to be completely eliminated. With regards to the surface finish, there appears to be a trend within a given orientation. The fully ground specimens tend to have a higher value than the as-built surface specimens. Now this is convoluted by the challenge in measuring the cross-section of with the as-built surface finish, and also the influence of the surface finish itself on the performance. But that's so those are the biggest takeaways here. So then now if you were to look into the effects of the process parameters itself, show me if you could go to the next slide, please. So here we were looking at linear energy density and looking at the influence of this varying linear energy density upon the different performance metrics. So one thing that was clear was there appears to be a downward trend for both yield and ultimate strength measurements, with increasing linear energy density. However, there you can see that there's quite a bit of scatter here. So this scatter is because of the anisotropy within the material. So if you were to segment this data set by test orientation, you'd see the scatter go down at each linear density. So the kind of complementary to this downward trend, we typically expect an increase in elongation. That might be the case, but we have a lot of scatter in the elongation data, and that trend is not really apparent. So this behavior here we theorize is, with increasing linear energy density, we see significant influences on the cooling rate, which thereby affect the phase transformation from martensite to close to equilibrium alpha beta phase, which is then in turn reflected in the tensile properties here. So observations seen here make sense, and they are in line with some of the observations in literature. So here we move to the next step. Next slide, please. Which is organizing the data, and in a fashion where you could read this into the BHM model for setup and training of the BHM model. So at different stages of the process, we've tracked various inputs or input variables, and we've also obtained different outputs and tracked them as well. So here in this flowchart, you see the different inputs and outputs gathered at different stages of the process, and how the process performance model dataset was put together, and how the process parameter microstructure model dataset was put together. So after this assimilation, we handed off the data to Yiming for BHM setup.
Thank you, Shrikar. So we have made the modeling efforts on 4 aspects. The first one is forward modeling to query the predictions at a given input. The input could be process parameter or microstructure, and the model has been evaluated with cross-validation. The second aspect is the variance-based global sensitivity analysis on the input parameter. Sensitivity analysis quantifies the influence of each input variable on the output parameters. And the third one is on inverse prediction and optimization. Inverse reverse to the process to find the inputs with desired output quantities. And prediction could be performed with setting up the target values. And the fourth part is intelligent data addition, which iteratively recommends the input parameter for additional testing. And this iterative process could be maximize our information gain with scoped budgets. Next slide, please. So the first challenge from the modeling is the design of experiments, and with a statistical method. We are doing it in a hybrid manner. The additive expert had identified the range for process parameters and recommend half budget based on their empirical judgment. And then we're using statistical method to propose the remaining half builds and to maximize the spatial distribution. And this method has been verified to be beneficial of our modeling accuracy. The DOE has been examined with visualization and also from the expert judgment. Next slide, please. This is a brief of the dataset for the thin wall feature. And we got 266 sets of specimen and 15 sets of process parameters and 90 data set from microstructure. And there are several interesting things to share with the group. And the data size actually vary with the output from experiments and measurements. Like, for example, we have 144 for illustrance and could be 250 for physical properties. And we considered 10 inputs and 6 for process parameters, and 4 for post-process, which are listed on the right figure. So this is the hierarchical inputs obtained in sequence. And the different measurements are collected, including mechanical properties, physical properties. So it's very informative for static modeling analysis. The table summarizes the association between inputs and outputs. Next slide, please. We have developed 3 types of the predictive model using BHM. The first one is from process to microstructure, and the second one is from microstructure to property models. The third one is from process to property models. And the MP model, which is short for microstructure to property model, is more general for guided design in general, and the PM model and the PP model could have higher accuracy for our identified few features. We have checked the model for cost validation, like shown below, and also produced the sensitivity analysis and checked their interactive plots to understand the physical insights. Next slide, please. This is some details for our evaluation of the developed PP model, which is short from process to properties. And for the PP model, we consider the about 9 inputs and predicting 4 mechanical properties. And the cost validation results are shown on the upper 3 figures. You can see the R square from cost validation is as high as like 0.88 and 0.82 for yield and tensile strength respectively, and which is very accurate considering the larger uncertainty from manufacturing material until the accumulated in the whole process. And another interesting observation is for the elongation, like you can see. Basically, we didn't capture much accuracy for the elongation. The R square is like 0.1. And so this could be something interesting to investigate for the future, either on the physical phenomenon and all other alternative modeling algorithm. And the global sensitivity has been produced and checked for each object respectively. You can see the sensitivity, the top few sensitivities could be used for the future designers to simplify their design process and allocate the resource on the most important factors. And the next slide, Neil, please. And here is a summary of the PM model and MP model details. And you can see like we have repeated this similar framework to develop properties for like microstructure, including volume, porosity, etc., and also from microstructure to property models. All the R square has been used as a threshold value to screen the accurate models, and we're using R square at 0.5 to as a threshold value to make the model acceptable or not. And the identified or acceptable models has been delivered in the final executables for user exploration. And another thing for the MP model is a little bit additional for the audience is the MP model has been include expert insights on how do we extract the input parameter, and there might be information missing from the CT scan to the microstructure quantities, and that could be something to explore further for the next step. And next step, please. Next slide. After developing the forward models for PM, MP, and PP, then we created the feature for inverse prediction and optimization. And the key concept is how do we identify the desired process parameters and motion parameters with given or identified mechanical properties, either with the target value or with just the identified properties for optimization. And the inverse prediction and optimization is essentially a heuristic optimization process. Basically, we iteratively call the forward prediction on the developed forward model and with efficient search of optimum parameters. So for the user usage, the user will input, for example, like the target yield strength as shown in the figure, or they just want to optimize the yield strength. Then the optimizer will be initiated based on robust objectives, either maximum likelihood or either maximum expected improvement to search for the optimum design process parameters. And in next slide, Neil, please. This slide gives a little bit more details on the algorithm. So like you can see, first step is the user input the target value or identify the properties of interest, and the optimizer will be initiated in an iterative manner using genetic algorithm, and it's a constrained multi-objective optimization. the constraint comes from the range of the process parameters and is accessible for the future user. And then the optimizer will iteratively call the forward model and evaluate the objective functions. We have implemented multiple objective functions for different conditions. And once the stopping criteria has been met, the recommendation of the process parameters will be outputted for the user evaluation. And in next slide, please. So after having the bidirectional models, including forward and backward, another piece is intelligent data addition. And for intelligent data addition, we have been using a software called IDIS, which is upon the forward model. And for this slide summarizes the basic flow chart. Basically, the user will collect the uninformed DOE, like from the design of experiments or the historical experience. And then we will collect the data, like either from build or defect analysis. And this initial data will be modeled using our BHM model and associated with the stochastic prediction. IDIS software will rank all the candidate points in the whole design space and recommend the most informative point for the user to be tested or built. And this process is iterative and more informative than the all-at-once design of experiments. And it also leverages the nature of BHM. So in this slide is our evaluation. In this slide is our evaluation of the in a hypothesis manner. So the left figure is the estimated uncertainty reduction with additional builds. You can see with the first 5 builds, and our uncertainty could be reduced almost by half. So this identified additional builds had been delivered to the additive experts and to be built and tested to augment our model and also do the validation. In next slide, please. This is give the audience a snippet of the additional builds, and we have added about like 10 builds for data for refine our model and also to validate our model accuracy. So we have the 2 sets to be keep in mind. The first one is for model refinement. The second one is for blind validation of our previous models. And this had been visually examined from the pairwise plot and the expert's judgment. Next slide, please. On the left figure is a quick validation of the validation data set collected from the additional test. And in the figure, the blue dots are our existing or original training data. The black lines are the validation points with the arrow bar. So the horizontal axis are the measurements for the yield strength. The vertical axis are the prediction. So we have you can see we have a 45-degree line, which indicates how consistent the prediction and accuracy match each other. So you can see in the plot, our prediction are conservative to cover all the true error, and which is very important for the safe design. And also accuracy-wise, it aligns with the overall trend of our training. And on the right figure is a concept called the conservative estimates with a lower 10th percentile, which has been enabled together with the mean value as a conservative estimate for the user's reference of their design. In next slide, please. The left figure is a quick comparison of our updated model and the original model or old model. And we have collected the uncertainty distribution in the whole design space using 100,000 data set. And the blue are the distribution of the old models. And the red are the distribution of the uncertainties from the updated models. Usually, smaller quantity, like a smaller uncertainty means like we are more confident about our model. Now you can see after having additional test, our uncertainty increased systematically in the whole design space, which is an indication of increased conservative, like our model have larger uncertainties to account for the additional tests from different machine setup, material loss, and test sites. And this additional source has been reflected by our increased uncertainties. So in next slide, please. The final piece of the modeling is a graphical user interface and the standalone executable. And the developed model of the validation has been incorporated in this executable. And basically, the user will have an iterative access to this bidirectional model with identify the model direction and the features, and also together with sensitivity plots. We're also using this executable to do some validation of the additional test. You can see in the bottom figure, one testing point. The experiment give us a value like 134, and our prediction is like 138. There is just like a 2 or 3% difference. And also, we provided the conservative is closer or much lower than the experiment for the user to have a safe design. Now I will switch to Shomo for the remaining talk.
Shrikar, actually. Shrikar, please.
Yep. Thank you. So switching gears a little bit, from the BHM model analysis, I'll take you through the model setup and framework for the other two features. The other two features being walls with discontinuity and walls with intersections and overhangs. Next slide, please. Right. So similar to feature one, we followed the process of coming up with a design for the thin wall with discontinuity, which we've kind of analyzed using simulation to avoid interactions between neighboring features inside the wall. Meaning, if there were two holes next to each other, we didn't want the building of one feature to influence the other. After doing that simulation, we've come up with tensile specimen extraction plans. And then we've proceeded to fabricating these walls. Next slide, please. So to go over the matrix for the thin wall with holes, we've had 6 different process parameter sets. Some of them were subsets from the thin wall build process conditions, and a few of them were IDACE predictions forecasted to improve the the process domain that was studied under this program. So we had 6 different wall layouts per process parameter, where we changed the whole shape between a rhombus and a teardrop and the overall geometry of the whole feature. So from this setup, we ended up with about 700 plus tensile specimen measurements, which we've used for creating BHM models and framework. So one of the challenge here was, how do you convert or how do you quantify this whole geometry in a model? To do that, we've further broken down this whole shape into basis features, which primarily compose of notches, divots, and microstructure or like skin effects. So if you were to take this the rhombus hole, you basically have 4 notches. So we sampled tensile coupons with these notches in the gauge volume, so we could assess the influence of the presence of this notch on performance. So a notch in itself has an included angle, and it also and the surfaces inside the notch can be a downskin surface, meaning it's looking down. It's the underside of an overhang surface, an upskin surface, which could be the face that is looking up. So we've come up with a nomenclature and variable structure to quantify these whole shapes into basis features. Right. So in extension, these 4 holes shown here end up being 12 different features. Next slide, please. So similar to build one, we've tracked data be input generated at different stages of the process, shown left to right here, and packaged it into 2 different data sets, the notch level data set and divot data set, which was then handed over to Yiming for simulation, BHM setup. Next slide, please. So just to quickly go over a first order evaluation of this data, if you were to pull all of the data and then segment it by the different notch types and different divot types, and this program for the notch data set, we ended up having specimens with AM notches, and to decouple the effect of the notch geometry and the AM surface finish, we came up with baseline specimens which had the same notch geometry machined into them. That way we could, uncouple the effect of the AM finish, and then take it and to further baseline it, have a specimen with no notch, so just so we can understand the effect of having just the machine notch. So similarly, we followed the same logic for divot samples, which is a curvature, a curved cutoff on the coupon. So if you have an AM divot, and if you had a similar geometry machined into the gauge length, which would be a machine divot, and then specimen with no divot. So if you were to segment the data set from all the different process conditions by these three flags, where AM notch, machined notch, no notch, AM divot, machine divot, no divot. One of the biggest takeaway is that from the AM samples, we see a decrease in performance and also a very big variation in overall performance. Now, if you were to compare it with machine notches or machine divots, you see a much less scatter in performance and also a slight improvement in performance. So here, one of the biggest takeaway is, with the AM surface finish, operating with that finish could significantly diminish your performance. Right. Next slide, please. So similar to the whole feature, we've designed the intersection wall geometry, followed that up with simulation to make sure it fits our conditions. Then we move to the specimen extraction plan and then proceed to fabricate it. Next slide, please. So here in this table, you have the different process conditions and used to fabricate these walls. So we modeled the matrix based on the thickness or the exact feature that was in the high pressure case. So we matched up the thicknesses in three different locations of the high pressure case and tried to build our experiment around it. Next slide, please. So we had two kinds of intersections, which you could call as a continuous X and a segmented X. So case A and case C are shown here, the two different intersection designs. So for the overhang features, we cut off the side inclined portions and cut specimens out of it. And to assess the influence of the intersection, we cut specimens at different orientation within the vertical trunk of the wall. And for the intersection region, we had the tensile coupons gauge length lined up as need be with the intersection region. So here we have, in the case A, you have the effect of building two intersections in that intersection union region. In case C, you have the effect of building one intersection in the intersection region. Similarly, the building of this overhang also affects the intersection region differently, and that was captured in the model setup as well. Next slide, please. Yep, similar to the other two features, we've simulated the data by tracking everything right from the design to fabrication to testing stages. Yep. So one of the takeaway from the intersection build was the anisotropy as seen in build one still persists, and just looking at the data, the presence of the intersections is not clearly seen here, but that is convoluted by a lot of different factors. But we didn't find any significant outliers, and the data looked good, which reasons then packaged and handed it over to Yimeng for BHM modeling. So here, next slide, please. So here I hand over to Shomo for further. Thank you.
Thanks, Shrikar. So I'll play this time-lapse video in the bottom left, shows just one example of the builds and how we achieved it. Using this study as the showcase, we thought of sharing the outcomes of the system level to be able to better explain the feature-based qualification methodology that we have developed, connecting the features to the build processes with the microstructure and defect characterizations and the material property relationships. To be able to validate and deploy this for a broader scale, we should understand the connections that we have from the heat input side in terms of energy densities, build strategies, feed speeds, etc., and also variabilities related to materials, machines, and testing. And also connect that to the feature build itself. So the different aspects of the feature and the identifiers of the feature itself that Shrikar talked about. So if you talk about just a thin vertical wall, the dimension of the wall itself. So if you look about the inclination, then you talk about the upstream and downstream surfaces, knot sensitivity. And then all of this rounds up with the thermal management of it, right? So how does the heat get extracted from the builds as in post-solidified state? So understanding the spatio-temporal data acquisition in terms of thermal history and the thermal gradient, which is a function of the microstructure and the property that we see. So Yiming talked about this multi-objective optimization toolkit using the Bayesian hybrid model, and I'm going to share some of the wins in terms of the cost and efficiency and the reliability as we drove down through it. And I have one slide where we can talk about the thermal visualization toolkit, where we had so we have made some important first steps. The goal is to connect the defects. So the goal would be to detect the defects and then connect the signals with the defects, and then have a closed loop system to be able to prevent the defects for the future. So if I go to the next slide here, really from the probabilistic machine learning part, it was a very efficient tool when we compare that with a conventional GOE. As you can see in the chart on the top, we were able to achieve the targeted predictions with 60% less sample space. That includes the fabrication and the calibration costs. Also, in terms of reliability, when compared with the linear regression, you can see that on your bottom right, that the BHM had as much as 50% better R-square number. So you can eat the cake and have it too, in the sense that you can have a lower cost and high efficient kind of model, along with the greater amount of reliability for the model itself. So from this slide, which is more looking at the thermography part of it, the details-based GUI tool was used to analyze the IR thermal data using these laser-based DED approaches. We utilized the IR camera from micro epsilon to capture the thermal history in a front view perspective. So that gave us a tremendous amount of opportunity to track the length and the depth of the hotspots in the deposition, observe the thermal history below the melt pool, which is also quite important, and then combining this information, we developed tools for analyzing spatial and temporal variations. So the tool was primarily developed at Youngstown State with assistance with EWI and GE. So Shrikar was the main person from GE who helped out with the tool. And the tool helps us identify the max temperature per pixels, time above threshold per pixel, and also average and integrated temperatures per pixel. So all of this are quantitative data. So in reality, we could have a potentially better BH model with this as an input for the future drives. The last chart here. So this is the grand summary of our thought process, which Neil had shared in the first few charts. This is basically the bridging the hows and the which and the what. So how did we build it versus which are the primary factors that we can analyze from the build itself, either during the build or during the post-processing conditions. And then ultimately, what is the performance in terms of the uniaxial tensile evolution? And all of this starts with the wide net that we cast in terms of the legacy builds and also some extended build parameters and build strategies, going through progressively in terms of the quantitative assessment of these and validation processes, including using a physics-based machine learning framework as the umbrella. So the Bayesian hybrid model plus the intelligent data addition was a great part of it which was helpful to generate various submodels connecting processing, microstructure, and property in an efficient and effective way. So hopefully this is a framework that we have adopted, and that could be further taken forward as a universal framework, which would be agnostic of the materials and modality of choice for future efforts. So that's all I have. And the last slide here is an acknowledgement of our efforts using the MAMLS program. Thank you for the sponsorship from Air Force Research Lab, and also the help with all the help from America Makes to be able to make coordinate through this project very smoothly. Neil, over to you.
So that really concludes our presentation. Is there any questions for the team?
All right, yeah. Just want to say thank you to Neil, Shomo, Srikar, and Yiming. We'll now head into the Q&A session. If you do have questions for our presenters and you have not done so already, please type them into the Q&A box. I do have a few questions here. So our first question, which software program was used for simulations and what simulation responses were checked?
Yiming, do you want to answer how, for the Bayesian hybrid model, what you used and what you did there?
First, I'm not sure if the simulation refers to the BHM. BHM is not a simulation; it's a predictive modeling.
Okay.
Yeah, it's based on Python.
So in the simulation portion, where Shomo was talking about where we simulated the build of the wall to identify what the stress patterns were and make sure that there was no overlaps between, no interactions between the stresses when we put the features in. That was called Simuflac. And it's basically it's an off-the-shelf program that we used, and they have an additive. Actually, they actually have an additive model as well.
All right, thanks, guys. Mm-hmm. So is that Python code available to the America Makes members?
The delivered executable is not. Didn't include the open source code.
Okay, thank you. All right, another question here. Do the data-driven or machine learning-based models had enough physics captured to extend this work to other AM processes, for example, laser powder bed fusion, or do all the experiments and measurements need to be repeated for different additive processes?
I'm sorry, would you repeat that again?
Yes. So do the data-driven or machine learning-based models have enough physics captured to extend this work to other AM processes, for example, laser powder bed fusion, or do all the experiments and measurements need to be repeated for different additive processes?
Maybe I can share a few sentences first. And we have three types of model: PP, PM, MP. And the MP model should be general and based on like microstructure characterizations. And in this way, it should be ideally it should be working for other types of predictions. But again, the training data set is from the DED, and we might miss a specific like last ignis, etc., and could be from other like a process.
So I would agree in theory, the microstructure to properties should be transferable, okay, but I think there are other physics that could come into, especially the heat, conduction paths and heat resist, heat conduction can come into play in between the difference between blown powder bed or blown powder and DMLM. So I don't think that's transferable.
Okay, thank you. Let's see. I think this is our last question here. Given the experiences of the team, do you believe there are opportunities of merit to create unique test specimen designs which may benefit future efforts for assessing AM product performance? And did that play a role in this work?
Shomo, you want to take that? You were.
Yeah, so that's a great question. So we really did that, right? We actually connected this the extraction strategies based on the feature that we chose. So in an ideal sense, we have to do that with a word of caution, because if you recall the microstructural hierarchy I'm talking about, so you shouldn't have a sample space which will interfere the size effects when you're trying to get the probability response. So if you can get if the representative volume element is representative of the microstructure, the overall microstructure, you would be able to have specific test geometry set up based on the what you're testing and what kind of feature that you're testing.
All right, thank you very much, guys. So let's see. I don't see any more questions coming in. So I think that will wrap up today's America Makes Project Closeout webinar. I would like to thank again Neil, Shomo, Srikar, and Yi Ming. If you have any further questions for the project team, please reach out to them directly at johnsonna@ge.com. That's Neil Johnson's email address. They'd be happy to answer any of your further questions. There will be a post-webinar survey going out to all those who participated. We really do appreciate the time you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. Thanks again for joining, and have a great day.
Thank you, guys.
Thank you.